Fun. It is quite a puzzle. This is 870 advantage shuffle. Okay, very simple short description. Those are usually problems that are quite simple, but that's not always the case. Okay, so you're given two integer arrays, nums1 and nums2. All right, with the advantage, You're given two integer arrays, nums1 and nums2, both of the same length, okay? The advantage of nums1 with respect to nums2 is the number of indices I for which nums1 of I is greater than nums2 of I, okay? Return any permutation. So permutation is any shuffling, some shuffling of the original array, right? You take all the original elements in the original array, and then you shuffle them around, meaning that you take one of the elements and put them in a new position, take the other element, put in another position, right? Shuffle them around. Return the permutation of nums1 that maximizes its advantage with respect to nums2. So what does that mean? You're going to have the most indices where the indice I, the element at indice I of nums1 is greater than the element at same indice I of nums2. Okay, so let's just quickly go over this example. All right, so in this example, we have nums1 equaling 2, 7, 11, 15, 2, 7, 11, 15, and we have nums2 equaling 1, 10, 4, 11. Okay, now what we're going to do in this problem is we're going to try to shuffle nums1 around such that for each of these, corresponding horizontal locations, the value nums1 is greater, strictly greater, than the value nums2. All right, and we're going to return that corresponding array, right? So for right now, we have something good going on here, right? Because 2 is greater than 1, so that looks nice. 7, 10, that does not work because 7 is less than 10. This works because 11 is greater than 4, and this works because 15 is greater than 11. All right, but we can actually make this even better because you'll notice that if we just swap 7 and 11 here, all right, if we just swap 7 and 11, meaning that we create a new array, right? But I'm really just swapping. You need to think about it in terms of swapping, right? Let's not think about it in terms of swapping just because it kind of complicates the way that we think about how we're supposed to think about this. We literally just take all these elements and we find a new location for them in the destination array that we're going to return, okay? And, well, you could just say, well, where can 2 go? Well, 2 was already good where it was, right? Because it was greater than 1, all right? Where can 7 go? Well, 7 wasn't good where it was, but it could go in front of 4, right? Because 7's greater than 4. 11, well, 11 can't even go where it used to be because we put 7 there, but 11's greater than 10, so we could put it there, right? And we could leave 15 where it's at as well, originally, right? So that's a new permutation of this nums1, which really just means, taking all the numbers in nums1 and putting them in some position, could be the same position as before. And that's our answer right here, right? So this is what we end up returning because, well, it turns out that every element is greater than. And I guess you could you switch locations of any of these things? No, you couldn't, right? Because, 2 has to go with 1, 11 with 10. 11 can't be switched over here, so this is the only solution. But sometimes there could be multiple solutions, right? If you could, it's not worth going down this rabbit hole too much, but if, this was like this, 3, 4, and 2, 1, well, 4, 3 would still be greater than 2, 1. So this order works, or, this order. So you just have to return any one of those permutations, okay? All right. So I don't think we need to do another example. I think the point is pretty clear here. Something to think about, though, is, well, what makes this problem kind of difficult, right? What is something that could occur in how you kind of logistically flow through the process of solving this problem, which could lead to an issue? And really what the issue is that, you might, for any one number, like when I have 2 here, right? Let's restart this problem. Let's look at it again, and let's determine what is the case that can make this problematic, right? So when I have 2 here and I want to place it again, so let's just go through this whole thing again so you can realize why there has to be some sort of sophistication in terms of what you choose and when you choose it. because you'll see here what happens, right? If I choose 2, well, I'm going to have to find somewhere for 2 to go, and the only place 2 can go is here, so that's fine, right? Now, let's just say that the next number I choose, let's just imagine the order of this was different. So 11, 7, 15. So it's the same elements, right? The order doesn't really matter of the original elements, right? Because we're going to end up putting them in any order we want. So let's say it was 2, 11, 7, 15. Now I have 2, right? All right, sorry, I have 11. And I say, you know what? 11 can go with 4, right? Because 11 can go, 11, when I match it up, they can't go with 1 because it's already occupied. It can go with 10, it can go with 4, and that's it. So I can choose either one, right? And I imagine I say, okay, I'll put 11 with 4. That works. But the problem with doing that is, well, even though 11 can match with 10 or 4, 11 should be with 10 because that will leave the opportunity for 7 to go in. Now 7 can't be placed somewhere where it can be with an element that protects it, right? I can still put 15 here. Right, so the order of which I put this determines, right, because this is just another permutation of the same thing, right, will determine how large of a solution I can create. So I need to be sophisticated. I need to be conscious of where I place elements because that's going to determine what the solution will look like when I complete the problem. So then how should we do this in order to ensure, like, you know, of course, efficiency and that we're not like taking up a space that could be better used by somebody else, right? Because that's really the problem here, right? The thing you should notice from this example is don't take up a place, even though the place works for 11, don't take up a place that someone else may need to use, okay? So how would you avoid this happening? Well, the reason why this happened is because I switched, when I started looking at these things, I switched looking at 11 and 7, right? Instead of 7, then 11, okay? Since I looked at 11 first, I didn't think about what might happen if something smaller like 7 came later. Okay, what I'm saying is, since I looked at 11, 11 had multiple options, right? It had multiple options available. But I didn't think about the consequences if 11 chose something and something later, which had less options, was unable to now make a selection, right? So what I'm trying to say here is, well, we should make selections in order, right? This wouldn't have happened if I checked 7 first. Because if I checked 7 first, I would have matched 7 with whoever was available to 7, and then 11 would have whatever is available left for it. And I guess kind of, you know, logically, if you want to think about this outside of this problem, making selections in order, one way to think about this, right, is imagine you have, I guess, let's just say we have a couple, we're trying to match people together, okay? All right. So we have people, and let's say, you know, this problem is really kind of similar to, say you have n men and n women, and all the women want to be with a man who's taller than them, and all the men want to be with a woman who's shorter than them, okay? So imagine you had these men, right? And, well, what you should do is you say, like, okay, you know, we should probably if we're trying to match these people together to ensure that, you know, if we're trying to make sure that everybody gets a match, well, the tall guy, right, and you probably noticed this in your life, right, the tall guy could be with anybody, right, because the tall guy is going to be taller than all the other people, right? So this guy here in the middle, he'll definitely be able to match with any of these people, right? So it's like, if we're not trying to maximize happiness, right? Maybe people don't want to be with people that are way different in their height, or, you know, maybe don't want us to be with a guy who's a quarter inch taller than them or whatever. But let's just say we're just trying to make everybody matched. Well, this tall guy is the least constrained guy, right? Because he's the tallest one, so he's going to be taller than everybody. And if he's not taller than everybody, then no one that's shorter than him will be taller than anybody either. So what we should first do is say, well, let's actually do this in order of height, right? We should first try to match the shortest guy, because anybody tall, if he can't match with somebody, maybe someone taller than him can, right? But we might as well give him an opportunity to see the most people, because he has the least likelihood of finding somebody that will meet his criteria. So let's not waste the person that meets his criteria on somebody taller. Let's try to get him matched first. Okay. It's a terrible way of explaining this. So maybe this person matches with them, Now this person comes in, but since this person's already occupied, right, they can match with them. And finally, you know, this person can match with them. Okay. So the idea here, right, is, you know, you should start with the smallest person, the smallest, I guess, blue character in this position, right? Because that smallest person will be the most constrained. So let them choose first, because anybody that they match, any subsequent person can also match. Okay, so it's not going to change the ordering. So you should always start searching in order. Okay, so maybe the first thing we should do in this problem is we should consider the nums in order, right? We should start with the smallest number and then work our way up, right? So if we start with 2, well, 2 is the most constrained person, so we'll match 2. Not 11 next, we check 7 next. 7 will find somebody that they can match with, and the only person they can match with. And if there were subsequent people, then it'd be the same. Now, what you might be asking is, well, what if there was an example like this? Let's say this was 100 instead. Okay. Well, let's do it another example. You can say, okay, well, although one argument you can make now is, okay, although the ordering makes sense, like I should try to get the most constrained person, right? The person with the least options first to try to match them. But what if that person with the least options, like, takes somebody else's match, right? Could that have a cascading effect on the other side? And I'll show you that it doesn't really matter, right? Because when we look at this example, you know, let's do this again, but let's say instead this was 100. Okay, and let's say we took the preemptive step of matching this first, of swapping this first. Well, you know, first again, 2 will go with 1. And then you'll say, okay, well, now that 7 took 4, 11's not going to get 4. 11's not going to get anybody. So now 11's not going to be able to be matched, right? And then 15 will go here, right? Or something else that would be bad is what you don't want to do here, right, is you don't want to put 11 in this place, right, because now you just screwed over 15, right? 11 is now a dud. 11 will not find somebody in the situation, so you need to put them somewhere where they won't cause a problem. So that's another side point that I just realized I should mention here, right? But the idea here is, well, now 11 won't be matched because 7 took their spot, right? But it doesn't, someone's going to get that spot, either 7 or 11, right? It doesn't really matter who it is as long as one of them gets it, right? We're trying to maximize the most amount of people that can get a match in this situation. We're not trying to, like, optimize for certain values. We're just trying to maximize the total number of values and get a spot. So that's the first point. Second point I kind of noticed is, well, you want to be very selective about where you put 11, right? Because you don't want to put 11 in a spot now that 15 is going to be stuck and 15 is going to be here and not going to be able to select somebody, right? You want to be able to put 11 somewhere such that, you know, 11's to the side, you put 15 in, maybe, and then you know, you backfill in 11 when things go bad. Okay, so let's continue down this line of thinking. So this problem here, right, we can always find the optimal solution. The problem is it's going to take big O of n squared time, right? And the reason why that's the case is, well, because for every element you need to find out where they can go, right? And you need to be conscious about, like, for each element you need to find the smallest thing it can match with, right? So you look at 2 and you find the smallest thing it can match with, then you look at 7 and find the smallest thing it can match with, et cetera, et cetera, et cetera, right? Because if the left side, right, if the man can match with a woman, if he can match with multiple women, he might as well match with the shortest one. That way, because any subsequent man will be taller, right? So any subsequent man will have everything available to them. Well, not the shortest. The shortest available, which would be the closest value to them. Right, but that'll make more sense in a second. So this is an n squared solution here, right? Because for each value we have to go through. But I guess what we could also do, try to make this even just a faster, is to think, well, you know, there's another way of thinking about this, right? So what if we took 2, 7, 11, 15, and then we also sorted this starting array here. So we said 1, 4, 11, 100, okay? So you should always match with the smallest person available to you. Now, of course, you're going to need to remap this up to the top, right? Because you have to map them back into the space that they're supposed to be, right? Because, you know, I've just shifted things around. Right now, 100's over here and 4's over here, but 1's in the same spot, okay? So what I should do instead is say, well, if I have both of these things sorted, I could say, you know, you should go with the shortest person that's available to you. 2, 1, 1's in this position up here, so then 2 stays here. 7 stays with 4. 4's in this position over here, so 7 goes over here. 11 can't go with 11 here, and there's nobody else available because the other people were taken, so this person gets discarded. 15 goes with 11, right? And 15 goes 11. 11's position was initially over here. And then the only thing remaining is 11 here. So you'll see there that that's actually linear time. And the reason why this makes it linear time is because, well, what's basically happening here, right, with this solution, what I'm basically saying we're going to do is let's take our guys in and we're going to sort them in terms of their height, right? And this guy, I guess, is just a ball. I don't know. And then remember we had our females here. What I'm basically doing here, right, is let's say, so I'm trying to find a nice little example here to make this work. And let's just say there's one lady who's, you know, extremely tall. So the initial idea, right, is that we would sort these guys and this person would go through and find their person. Then this person would go through and find their person. But what I'm now saying is, well, why don't we also sort the people we're trying to connect to, right? And if we start these people in order, right, if we look at this guy first and say, all right, is there anybody you can match with, right? I say, yeah, this person, right? And these people go off and they're on their merry way and they're happy. All right? Now this person comes in and the first person he counters is the shortest person and they can match. So they go off on their merry way. Then this person goes in and this person notices the first girl that's available, he's shorter than. Okay? Now the reason why this makes it more efficient is at this point, if you're shorter than the shortest person available, then all the subsequent people are also going to be too tall for you. Right? So since these two people already matched off, I can't choose them. And if I'm shorter than the shortest person available, I don't need to keep looking through the whole system because I already know I'm shorter than the shortest person available. There's not going to be anybody for me. Right? So then these people match off, and then at the end, we match these people together, but they're not actually, you know, a unit. Okay, so you got to go through what I did here again. Right? What I'm saying is, you know, I don't need to look through the whole array. I just need to look at the shortest person available. And if I can match with them, then that's good, and I'll move on. Right? Because any taller person, it could or could not. Maybe I swap, right? Maybe two people can swap with each other. But if I can match with the shortest person, we can go off, and that's going to give me +1. It's going to be the same situation. And if I can't match with the shortest person, I don't need to keep looking through the system because I already know that's the shortest person available for me. So if I can't match with them, I'm not going to be able to match with anybody. Right? So that's the same thing up here. Right? The case up here is, well, if I can't match with something on the right and it's already sorted, I can't match with any of the subsequent elements either, so I might as well not try. Okay, so let's go ahead and write the code for this. You know, what we're really doing, and that's going to be n log n, you know, time in this situation, because we just need to sort the two things and then go through it n time. So how will we do this? Well, hopefully I can click in. It's not letting me. Very weird. All right. All right, so I'm in. All right, so I'm actually going to disconnect my tablet because it causes some computational issues. And, well, let's sort nums1. All right, now something we need to think about with nums2 is that, well, we had to be conscious of where elements will go on the end, right? Because we want to sort nums2, but we also want to position elements in nums1 in the right places accordingly. So we can't just sort nums2 because we have to know the order of the elements when we make a decision about where things go, right? So what I'll do is I'll create this just index array, and I'll say index array equals sorted. We'll do the range of nums1, range of length of nums1. Right, and then the key will be for each of the indexes, its position in nums2. Okay. Now we just look at each number in order. Right, so we'll look at each num in nums1. So we'll just call that boy, because we're going to do boy and girl, right? So for each boy in nums1, we'll just say, so I'm trying to think about the best way of doing this. So I'm going to reverse the order. I'm wondering if I should reverse this. I'm thinking about on the spot how I'm going to do this. So sorry if I'm, well, I don't need to call reverse, just make this negative. Because I'm trying to pop from the end. So if I can match with this, so this I'm going to check, can this boy match with the shortest available girl? Right, that's basically what I'm doing here. Girl. All right. So if boy is less than, the boy is taller than the shortest available girl. So if he's greater than the shortest girl available, which would be nums2 at I of -1. Because I of -1 is the smallest element, right? That's the index of the smallest thing available. Okay, because this is the range. So this would be the smallest element. That would be the index of the smallest element. So the index of the smallest element at nums2. So that would be the, I'm going to just write it out, okay? Because this is a pretty complicated solution, so I don't want to get all finicky and specific. So that's the smallest person. If the boy's larger than her, then this is a good solution. So then we could say, all right, in our res array, we'll do res array equals -1 for, it'd be the length of nums. Nums1. I'm sorry, guys. I'm all over the place today. This is not a good solution for me. So if I'm taller than the shortest girl available, then I'll just say, okay, if I'm taller than the shortest girl available, then we can be matched together. So that means in the solution at the index of where that girl was, it's going to be this boy. And then I'm going to pop. And that'll be popped from the array. So that'd be, say, I pop -1. All right. Otherwise, this boy isn't going to be able to find anybody, right? This boy can't match with the smallest girl, so he's not good. So for now, we won't do anything. But we'll print out res, and you'll see the problem that still remains, right? And then return res. I think there won't be a problem with this one, actually, because everybody can be matched. So when you do it this way, it actually works. Nothing worse than something actually working, right? Right, so this actually might, I mean, actually I don't know, because, okay, this is wrong. Range length of nums2 key equals lambda. Key equals, sorry guys, lambda index. And the function. Why did I do 2? Bram, suffering from a aneurysm or something. I hate this new format. Okay, so case 1 passed. Okay, so case 1 passed, right? The problem with case 2, right, because in case 2, someone gets discarded, right? Who is it that gets discarded? So 12 finds a match. Or no, 12 finds a match, 24 finds a match, and 32 finds a match. So there's no match for 8, right? Because 8 is the first element you see, and then it tries to get matched with 11. It can't get matched with 11, right? Because 11's bigger than it, and 11's the smallest one of the girls, so the boy can't be matched with any girl, so we have to discard them. Right? So how do we... Where do we put this thing, right? Where do we put elements that don't find a friend? So maybe we should make this thing a deck. And then we don't need to reverse it. Okay? Because if we find somebody who can't find a girlfriend, right? Like in the example we had, the shortest like a short person ended up with a really tall girl, right? Because if someone can't find somebody, that means there's going to be a slot that's empty, right? There's going to be a slot where we don't get a match, right? There's going to be, if I have N boys and N girls, and one of the boys can't find a match, well, that means one of the girls is not going to be able to find a match. So we might as well put that boy with the tallest girl, because the tallest girl is the least likely one to find a match. And if the tallest girl can find a match, then someone shorter than them can also find a match. So we might as well put that shortest available boy with the shortest available girl. So what we'll do to do that is say if the boy is greater than the girl, then we'll put them together. So I think that's just a regular pop. But if the boy doesn't work, then we're going to say, all right, sorry, this boy can't find a match. So we're going to put you with the tallest available girl because that's the least likely person to be able to find a match. So that'd be pop left. I don't remember if it's pop left like that equals the boy. Oh, no, but it would still be... Now the order is opposite, right? So this would be pop left, and this would be pop... Max! So my dog is losing his mind. Right, this will be pop because I changed the order now. So now the smallest girl is at the very left, which makes sense, right? The smallest one should be left. The largest one should be at the right. Oh, but then this is still... Oh, my gosh. Sorry, guys. Sorry. Now this is at 0. All right, okay. There we go. It's funny because this isn't actually the original way that I solved this. It had the same runtime, but I was using like 2 while loops and then moving things around, and it's kind of ugly. So it's kind of funny that, doing this again, even though I wasn't able to articulate how you solve it appropriately, I mean, I wasn't able to articulate it sufficiently, at least in my mind. It's funny that I actually ended up writing something that's a little bit cleaner. And I'll show you my old code right now after I do the runtime if anybody's curious. But so what is the runtime? So we have to sort nums1, that's n log n time. Right? We have to sort nums2, another n log n time. We have to create this deck, so that's n space. We have to create this return array, which is n space. Maybe, I don't know how you would, that'd be a fun little exercise. Try to get the space down by, moving your res solution into the array given and then return the array given, or, but you still have to create this deck. So how are you going to constant space? It doesn't really matter. What I'm basically saying is like, you always have to create at least n space to create this deck. And I don't think there's any way to not create something of n space. Well, it's the indexes of things. Yeah, I don't think there's a way. So this is going to take n space, n log n time, and then for n elements, you do 3 constant checks. Pop left is constant, pop right is constant. That's why we did it this way. And yeah, so that's n log n time, n space. So let's just write that down. So say n is the length of nums1. For time, we have n log n. And for space, we have n. Okay. So what was my old solution for those that are curious? Let's see this. 2 hours ago. Dude, I get so annoyed by, like, sometimes Leetcode, I feel like they force me. I don't know what their deal is, but they like force me to use the new GUI, and I'm just not interested, right? I've never had an issue with the old GUI. I guess this looks a little bit nicer, but I don't think it's worth the cost associated with its performance. I don't like the multiple case kind of situation. I don't like how this looks, actually. But yeah, this was my old approach. So I created 2 eyes. I had these 3 variables. It's basically doing the same thing, but this is a little bit cleaner because I thought about the fact of, the smallest boy should go with the largest girl if the smallest boy can't find a match. All right. So that's it, everybody. I hope you have a beautiful rest of your day. Bye-bye.